All right, guys, welcome back. Here we go with lecture video, technically number 3 here, on titration. Now, for a lot of you guys, you've already done a titration lab, so this isn't going to really be a foreign concept to you, but we're going to talk about some of the more of the raw science behind a titration rather than like the physical nature of doing an actual experiment surrounding a titration. So a little bit of a different type of scenario here. So let's get right into it. Process of adding measured values of an acid or base of known concentration to an acid or base of unknown concentration until neutralization occurs. And at this point, guys, we all know what neutralization is. Neutralization, again, is when you mix equal parts acid with equal parts base, and they neutralize, keyword there, neutralize to becoming neutral pH, because they essentially create water from their reactants here, right? Obviously, in our case here, guys, in the lab you guys recently did, we took an acid of known concentration, right? So an acid of known concentration, and added that to what essentially ended up being a base of unknown concentration. That's what we did in our lab. Sometimes you flip the script. Sometimes you have a base with known concentration and an acid with unknown concentration, and you have to discover and figure out what the concentration then is of the acid instead. So a little bit of a different scenario here, but ultimately still the same point here. You take what you know to find out what you don't know, and that's basically what a titration is in a nutshell. Okay. Now, every single titration, guys, always boils down to one thing: the equivalence point, the point at which neutralization actually occurs. Now, that's exactly what equivalence points is. It's the point where neutralization actually occurs. So at equivalence point, the number of moles of the H+ ions that we all at this point know are associated with acid exactly equals the number of moles of the OH- ions that we all at this point know exactly equal our base. So acid equals base exactly, and there you go. Okay, so neutralization occurs at this equivalence point here, where all the acid you've got equals all the base you've got, and now you're essentially just forming water. Okay, so equal amounts of acid and base have been added. Now, what are the steps in a titration? Again, we already basically know the steps in a titration, but they are here just to kind of run you through them. Now, endpoint. Endpoint is another very important different type of point that you run into in a titration, especially whenever you're using a very, very specific indicator, an acid-base indicator, just like you guys use or are going to use in your phenolphthalein that you've used. Okay, now, endpoint is the point at which the indicator changes color. Okay, endpoint has nothing really at all to do with the acid or the base specifically. All it does is help you monitor the change in pH here. So the endpoint is the point at which the indicator officially changes its color, right? So all the different color changes that you can possibly see on table M in your reference tables from all the indicators, or the 6 different indicators that are on table M there, right? Again, that's your endpoint, right? So if you've got, for example, let me grab my table M here. For example here, if you're looking at table M, let's take a look at the very, very first one here at the very top, methyl orange, right? Methyl orange has a pH range, which I think I can read as 3.1 to 4.4. So if this pH, essentially changes from 3.1 to 4.4, this is the color change you get from red to yellow. Right, so that's essentially what occurs here. You get a red to yellow change. So that's your endpoint, the point at which the indicator changes color. So if you add some methyl orange to some solution, and your solution is, red, then you're going to obviously know that you've got a pretty acidic solution. But if you start adding some type of other solution to it, until it eventually changes colors from red to yellow, that is called endpoint. Whenever your indicator in question changes its color. Now, how is it that, specifically for our lab that we're doing in class right now, our titration lab, why is it we use our phenolphthalein indicator specifically for this lab and not something like methyl orange or bromocresol green or any of the other funky named indicators on table M there? Well, again, it's incredibly important to make sure you pick an indicator for which the equivalence point is right near the end point. Okay, the end point is very, very close to the equivalence point. Okay, you want to make sure that your indicator is changing colors when you are reaching the equivalence point, right? When neutralization is occurring. Okay, if the indicator doesn't change colors, when the neutralization occurs, that's going to make it very difficult to tell you guys when to stop adding your amount of base, in this case here, right? Because the thing you're looking for was that really, really nice looking, cool pink color, right, in lab. Because, again, we're using phenolphthalein. Again, that's a really great indicator because the presence of that pink tells us exactly when to stop adding all of our base. Because the end point, the point at which our indicator of phenolphthalein changes color, is exactly right near the equivalence point of reaching a neutral pH of essentially 7. Okay. So for most titrations we do, the equivalence point is, of course, at a pH of 7, because the equivalence point is going to be a representation of neutralization, which is a pH of 7. And so phenolphthalein changes at a pH of 8 upwards of 10. And since it's right at a pH of 8, that's a pretty darn good indicator to tell us that, hey, endpoint is super close to a pH of 7, so therefore we can absolutely use it. So for example here, question reads, what is a suitable indicator for a substance with an endpoint of 8.4? Well, if we're looking at our table M here, we need to make sure that our endpoint is super, super close to an indicator that's going to kind of match that. So in this case here, phenolphthalein or Thymoblue are going to be great indicators for this case here, right? If the endpoint we're looking for is a color change of 8.4 pH, well, we just have to make sure that we are picking an indicator that has a pH range that 8.4 is going to be in between or super close by. So if we look at phenolphthalein, for example, phenolphthalein has a pH range of 8 to 9. 8.4 is right in the middle of that. Okay. Again, still looking at our next one here, which was Thymoblue. Thymoblue has a pH range of 8.0 to 9.6. Okay, a little bit of a wider range here. Okay, a little bit of a wider range here in this case here. But again, 8.4 is still in the middle of 8.0 and 9.6. So therefore, Thymoblue can still be used when it comes to different titration equations. But phenolphthalein is used a lot more often than Thymoblue for sure. Okay. What about an endpoint of 5.4? Again, endpoint of 5.4 needs to be in between the pH of the indicator's range. In this case here, Brome-Cressyl green is going to be the one to utilize here. Brome-Cressyl green has a pH range right here. That's a 3.8 to 5.4. Okay, our endpoint is exactly right there at 5.4. So therefore, our Brome-Cressyl green is going to be clutch there for that reason. Okay. Titration calculations. Now, the purpose, again, of a titration is to determine the concentration of your unknown, right? Again, the lab you guys are doing or have done already had a known acid and an unknown base. So our goal has always been to find the concentration of the unknown base, right? Whether it was base Y or base G or base K, base O, base R, whatever, okay? That was your goal, and that is your goal for a titrations lab. The equation you guys are going to utilize, like I mentioned in class, is this guy right here. MAVA equals MBVB. It's the same exact equation that you guys used in the past, back in chapter 13. And conveniently enough, guys, it's also right here on table T. So it makes your life also a heck of a lot easier, because right down there at the titration spot on table T here, right, is your equation. Here's the word titration right here. And then, of course, here's the equation MAVA equals MBVB. And then, obviously, everything right there is explained, right? MA is your molarity of acid, VA is your volume of acid, MB is your molarity of base, and then VB is your volume of your base, and you're good to go. Okay, so MAVA equals MBVB is your go-to equation. We'll probably do a couple examples of this guy in class. Okay. Now, the very last thing we're going to talk about, and then we're going to close up on chapter 14 here, rather, is what's known as a buffer. Buffers aren't really utilized, and they're not super important for the purpose of this class here. But if you go, do take anything, in the future, if you take AP Chem or if you take any kind of chemistry class or biochemistry class in the future, buffers are incredibly important. Okay. Now, what is a buffer? A buffer is a solution that resists changes in pH when limited amounts of acid and base are added. Essentially, guys, it's a solution that buffers. It doesn't really allow for much change to occur. It's very pH resistant. Okay. Even when you add acid or when you add base to that solution of buffer. Okay. Essentially, it occurs when a neutralization reaction where equilibrium forms, right? So, for example, in our blood, guys, there's actually hydrogen carbonate, which is H2CO3. It's a type of it's H2CO3. It's a type of acid essentially that's in our blood. That's used as a sort of a buffer because it's going to help maintain the equilibrium in our bodies so that the pH of our body and our blood doesn't really change all that much, right? It's really important, and you guys learned this obviously last year in your biology class or recently in your biology class. The idea and the concepts surrounding homeostasis, right, and making sure that the body can maintain perfect pH or near perfect pH at all times, and that's obviously very much in alignment with the idea of homeostasis. Now, this hydrogen carbonate being present in our blood allows for any kind of radical changes in our pH to not really happen all that often, right? It allows to essentially buffer any incoming acids or incoming bases to allow for the pH of our blood to really stay and maintain the pH it needs, and that's gonna basically be where we call it a day today, guys. Thanks so much, and I'll see you in class.